Hi everyone, I'm Rowan, one of the specialists here at UCT, and we're going to be talking about the gas laws today. These aren't the most exciting things to learn, but they do have practical implication, and that always makes things a bit easier if you can sort of see how they apply to your day and to your work. And if you asked me, how should we go about learning these laws? I would say the approach is first learn the definitions. They're just definitions. You need short, punchy definitions for all of these things that you can just blurt out in your sleep. So, you're in the middle of the 3 a.m. tibial nail and somebody says, what's the definition of a gas? Boom, and you can just say it, no matter how fast asleep you are at the time. And the point is that you use those definitions to kind of lay the framework or lay the skeleton onto which you hang the meat of your learning. And so after you've learned the definitions, then you learn the equations. And that's it. You've just got to learn the equation, learn the law. And you've got to be able to just blurt that out again, even if it's the middle of a neuro case at 4 o'clock in the morning. But I would suggest that you link your learning of the equations to the learning of an example that explains what the law means, just something to help pin your memory on. And then you want to practice. You want to practice using the equations to solve problems. It's maths, right? It's not fun, but it's maths. So for those of you to whom the equations come easy, that'll be fine. For those of you who struggle, you really do need to practice. And I suspect that's how most of your questions will come in the exam, is in terms of equations that you have to solve, calculations of volumes of gas or pressures of gas or temperatures or implications of changes in different parameters. So go to past papers, find those questions, go online, find questions, and practice them. I've also put a bunch of references at the end of this talk. Guys, I don't think I can explain this stuff better than, say, the Khan Academy or the College of Anesthesia in the UK, or multiple other articles, YouTube videos, clips that have been made to describe these things. And so I'm going to keep it very simple, but I would suggest that you go to the references that are in the bottom of the paper, bottom of the talk, and just Google them. Khan Academy is a great place to learn this kind of thing. Right, so let's start with the definitions. What's a gas? So a gas is a substance existing in its gaseous phase above a critical temperature. And what's its critical temperature? Well, the critical temperature is the temperature at which a gas cannot be liquefied, no matter how high the pressure applied to it is. Okay, so if a gas is a substance above its critical temperature, then what's a substance in its gaseous phase below the critical temperature, where if you do apply pressure to it, it can liquefy? Well, that's a vapor. So that's what we work with daily. If we apply enough pressure to our vapors, they will liquefy. Right. But what's pressure? So pressure is a measure of the force being applied to a substance per unit area. So if you're pushing down on the plunger of a syringe and you measure the force you're applying with your thumb on the top of that, the area over the top of the syringe, that gives you pressure. It's measured in pascals. But remember that the pressure in a system, in a gas, is equal throughout that system. No matter which surface of that container holding the gas you measure the pressure, or even if you put some sort of pressure measurer in the middle of the gas, the pressure will be the same everywhere. What's temperature? I've always struggled with this definition, but it's the average kinetic energy in a system. And essentially it translates to a measure of the degree of hotness or coldness within a system. What's volume? I mean, it's very simple. It's what you think it is. It's the space occupied by a thing. it's a three-dimensional measure of the space occupied by a thing, sometimes also described in terms of how much liquid that thing can displace. Think of Eureka running down the street in the nick, shouting, I've got it, I've got it. His name wasn't Eureka. That's just what he shouted. Sorry about that. Okay, so we're going to move on to the gas laws, the reason we came here. But just to say that gas laws describe the behavior of gases, but they actually only describe the behavior of something called an ideal gas. An ideal gas is a gas that obeys all the gas laws, but they don't actually exist, because real gases, at the extremes of pressure and temperature, their behavior gets funky and it changes, and they don't obey the gas laws perfectly. So the first gas law we're going to talk about is Boyle's law, and it states fairly simply, for a fixed mass of gas at constant temperature, the pressure is inversely proportional to the volume of that gas. And so you can write it as pressure P is proportional to 1 over V volume, or pressure times volume is a constant. And so if you take the same mass of gas and you keep it at a constant temperature, but you change the pressure or the volume, the other will change proportion. So you can write that third equation, P1 V1 is equal to P2 V2, where the P1 V1 is the pressure and volume of a gas in its first container, if you will, and P2 and V2 is the pressure and volume of the gas in its second container. So a practical implication, those of you who are involved in air transfer of patients on ventilators will know that before you take your patient up into high altitude, you need to swap out the air in the ETT cuff with saline, because as you rise up in your aeroplane or helicopter, the atmospheric pressure changes, and the pressure on the cuff changes, and so the volume of that cuff will increase as the pressure goes down. And that can obviously cause trauma to patients. Equally, in hyperbaric therapy of patients who are intubated, saline is used in the cuff because as the pressure, atmospheric pressure, the pressure in the cuff increases, an air-filled cuff would decrease in volume and lead to leaks around the cuff, and so saline is used, which is incompressible because it's a liquid. Boyle's law. The next law described as Charles' law, which states for a fixed mass of gas under constant pressure, so the mass of gas, the number of moles or molecules of that gas stays the same. Under constant pressure, the pressure in that gas system stays the same. The temperature of the gas varies directly with the volume of the gas. So as you raise the temperature, so the volume goes up. That can be written as V volume is proportional to T temperature, or volume over temperature is a constant. And again, if we take the same mass of gas under constant pressure and we change the volume or the temperature, they will change in proportion, and so V1 over T1 is equal to V2 over V2. So if you take a balloon, now I couldn't think of a clinically practical example that worked nicely for me, but if you think of a balloon filled with a amount of gas and then sealed, and then you move that balloon into the fridge, you keep the volume of the you keep the number of moles of the gas the same, and you keep the pressure of the gas the same, assuming some things about how elastic a balloon is. But if you keep those two things the same, and you keep the atmospheric pressure around the balloon the same, then as the temperature of the gas in the balloon changes, so the volume of that balloon will go down and the balloon will shrink. Think of your packet of chips that you buy in the airport. You climb into a plane, and as you fly up to high altitude, and atmospheric pressure around the packet of chips, and therefore within the packet of chips, decreases, so the packet of chips expands. Charles law. Okay, now some texts talk about Gay-Lussac's law, Gay being a different person from Lussac, and I think if you're French, then some people claim the French discoverer. If you're English, then they claim the English discoverer. But others just talk about the pressure law. I'm not here to fight that fight. But the third gas law states that for a fixed mass of gas, now at constant volume, so the same, you keep your molecules the same, you keep your volume of the gas the same, the pressure is directly proportional to the temperature. Right, so if you put some gas in a cylinder and you heat the cylinder, the pressure in that cylinder will go up because the volume can't change within the cylinder. We can write that as pressure is proportional to temperature, P is proportional to T, or P over T is equal to constant. And again, if we take that cylinder example, so we keep gas in there which has the same number of molecules in it, that doesn't change, and the volume of the cylinder doesn't change, and then we heat it, so we change the temperature, right? So P1 T1 equals a pressure of 100 kilopascals at room temperature. P2 T2, you change the temperature of that cylinder by using a flame or putting it in an oven, the pressure will go up, which is why many gas cylinders have pressure relief valves, so that in case for some reason they start to overheat and the pressure goes beyond a certain point, a pop-off release valve pops and gas escapes to relieve the pressure and prevent an explosion. It's akin to a pressure relief valve on a pressure cooker device, except that obviously with pressure cooker devices we're talking about water and we're not above water's critical temperature, so it's a little bit tricksy to equate the two of them perfectly. Okay, so Avogadro's law. Why somebody with a name as weird as Avogadro managed to imprint himself onto science into perpetuity, is a bit of a mystery to me, but there you have it. Avogadro's law about gases. So if you have two different kinds of gases, right, and they're in a container, and the container has the same temperature and pressure within that container, and the volume of that container is the same. So Avogadro's law states that under the same conditions of temperature and pressure, equal volumes of different gases contain the same number of molecules. Okay, and if we follow through on that equation, talk about it a different way, what that means is at standard temperature and pressure, so 0 degrees centigrade, 1 atmosphere, 1 gram mole of any gas occupies about 22.4 liters of volume. Okay, so that's quite interesting. So it's two different gases at the same temperature, pressure, and the same volume have the same number of molecules in them. So you will have noted that all four of the laws we've discussed deal with the same four parameters of a gas. It's the, where's my hand? It's the mass, the number of moles of a gas, the temperature of that gas, the volume of that gas, and the pressure of that gas. So if we take all of those four parameters and try to smush them together mathematically, or as experimental scientists did some time ago, they came up with a constant that allows the equation to be true, and an equation that looks like this. For that given amount of gas, the pressure in that gas times by the volume it occupies is equal to the number of moles of gas, the number of molecules of gas there, times by this universal gas constant, 8.31, times by the temperature of that gas. And that's the ideal gas law. Again, you've got to learn it, and you've got to try and memorize what it means. But what may help you is if we start to apply it. And so I'm going to try and answer a classic question about the universal gas law in the next slide, it's something that comes up a lot, and it's trying to work out the volume of gas available to you from that stored within an oxygen cylinder. Right, so the question says, how long will the size E oxygen cylinder filled to 13,700 pascals last? Okay, so we've got essentially two systems here. We've got the system where a set number of gas molecules are contained within a cylinder, and then we're going to release those gas molecules slowly from the cylinder through some tubing to the end of an ET tube, which is placed inside somebody's trachea. So two systems, but we're going to assume that the number of molecules of gas in that system is the same. It's the same amount of gas that we're just pouring from the cylinder into the patient, and we're going to assume that the temperature doesn't change. HMEs and etc. excluded. So if the temperature is kept the same, how do we work this out? Right. So let's talk about the E-sized cylinder. Right. So if we look at P1 V1 is equal to N1 R1 T1 for the first system, the E-sized cylinder, we know what the pressure is because it's measured. The valve on the cylinder tells us that we've got 13,700 pascals of pressure in the cylinder. And we know what the volume of an oxygen cylinder, an E-sized oxygen cylinder is. It's 4.7 liters, right? That's something we can memorize. We can read it on the cylinder. If we look at the patient end, gas is going to emerge from the end of the ET tube at atmospheric pressure. Let's call it 101 pascals. But what we're trying to work out is how much volume we'll now have. How many liters of oxygen we can deliver to the patient, considering we've only got 4.7 liters of oxygen, but at really high pressure in the cylinder. Right, so if we move down to the second box, you'll see that R, the gas constant, is obviously the same for both systems, 8.31. The number of moles of gas, the number of molecules of gas, N, is the same in the cylinder and as it is released into the patient. And we're going to assume that the temperature doesn't change. So we can then say P1 V1 is equal to P2 V2. We know what the pressure is in the cylinder, 13,700 pascals, and the volume is 4.7 liters. And we know what the pressure will be at the patient, 101 pascals. Bit of maths, and we get 638 liters. So if you take a 4.7 liter oxygen cylinder filled to 13,700 pascals, and you pour it out into the air, at atmospheric pressure, you will pour out 638 liters. So at basal use, we know this is from physiology, we know that humans use 250 moles per minute of oxygen at absolute basal conditions, and so we divide 638 liters by 250 moles per minute, and we get 42.5 hours. So that's how long the cylinder will last if we're just using it at basal flow. But if we turn that cylinder open to 15 liters per minute, because we are using it with an ambu bag or to drive a ventilator that needs really high flow, if our consumption is 15 liters per minute, then you'll see we'll only get 40 minutes out of that cylinder. I hope that makes sense. You've got to practice this. You've got to try a bunch of different examples until it starts to feel comfortable and make sense to you. Okay. A slightly unrelated law, but still considered, often packaged within these gas laws, is Dalton's law of partial pressure, and that simply states that the total pressure of a gas mixture is the sum of the pressures of each of the gases if they existed on their own. So if you take a container and it's got multiple different gases in it, the total pressure within that gas will equal the same as the pressure exerted by gas 1 and by gas 2 and by gas 3 and gas 4. So this has practical implications for us if we think of delivering anesthesia at different atmospheric pressures, which occurs when we deliver anesthesia or anesthesia gases at different altitudes, where the concentration of gas that you're trying to deliver may stay the same, but the partial pressure that you deliver actually changes. And I'm going to commend to you an article in the BJA, an editorial from a couple of years ago written by Prof. James and Ross Hofmeyer, and they explain it much better than I do. The link is in the references. read that article, and that should help explain how these things shift over time. And these are the references that I've used to create this talk. So I hope that little journey helps you get a very succinct framework of what the gas laws are, but I really commend to you the idea of going and practicing using these equations to make them stick in your head. Good luck with your exams, guys. This really is the biggest hurdle, and life gets better after part 1.